All right, good morning. It's Miss Muscarella. Who do I have so far here in the in class? Ooh, here, crying baby. All right, can you hear me now, Rachel?
Yeah.
All right, cool. We can hear you too. Hey, Lauren. All right. Well, just in case like it doesn't, you can't hear anything, you can just go ahead and type it in that chat window right there.
Okay.
All right. Now, I wanted to go over a couple of things, but before I do that, what kind of questions did you have so far on anything?
Point of inflection, probably.
Point of inflection. All right, cool. So with points of inflection, is it finding them or looking at them from a graph or which piece?
Probably just finding them. I'm on the quizzes. I got some of them right with the graph, but just the math of actually trying to find them, I was a little confused on.
All right, cool. So if you have the graph, and this is where you have to be really careful. So this is one of the ones from the quizzes. That was on there. Now the critical thing right here, it says, all right, this is a derivative right here. So anytime you have the derivative function that's graphed, what you want to look for are just wherever the horizontal tangents are, or the first derivative. So anywhere you've got that horizontal tangent line, like, hey, right there, that's going to be an inflection point. Right up here, x equals 0 is going to be 1, and then over here, x equals 1. So those would be the three points of inflection just based off the graph. Does that make a little more sense now?
Yeah.
Yeah. So that's where you have to just really be careful if you got the graph of the derivative that you're looking at, or if you're looking at the graph of the original function.
Okay.
Now, if you're looking at the second derivative graph, you what you want to do is find the zeros. Like if this picture right here with a second derivative graph, then you would just look at wherever the zeros are, and that would be a critical value at x equals -3. -1 would be a critical value, and so would 1. Those are not critical values, but they would be points of inflection. Does that make sense?
Yeah.
Thank
you.
Yeah, absolutely. Absolutely. Hey, good morning, Jessica. How are you doing today? Ooh, everybody just got muted. Yeah, so that's just that piece right there. What else do you guys have questions on?
Can you hear me?
Yep, we can hear you.
Oh,
How you
morning.
doing, Jess? Good morning.
Good morning.
I can't believe we
Okay.
got another snow day. This is amazing.
I don't know why. I don't know if I'm happy about it.
Yeah, I know. If we had break wasn't coming up, I think it'd be okay. But now everybody's going to be even more stressed.
Yeah, I'm stressed for the blood drive because I want it to happen, and I don't want it to get canceled.
Which day is that one on? Is that one on Wednesday or Thursday?
Wednesday.
Wednesday? Yeah, I don't think that'll end up being canceled unless
No,
school.
hopefully not.
Yeah, if school's canceled, then we'll have an issue. But
well, maybe they can get the people to still come in.
Yeah, they might. They might. All right. So, what kind of questions you got, Jessica? Before I go over a couple of things.
Okay. Well, so the text you sent me last night said point of inflection was the min or max of the derivative graph.
Right. Yeah. So that's like this function right here. So right here we've got a minimum right there, a maximum right there, and a minimum right there. So those two, or those three values, those would be the POIs there if this is your derivative graph. So what
the POIs of the the normal function.
Correct. Yeah.
Mm-hmm. So you would just know that's where it changes from concave up or down or all that, but that's like an extra thing because first you'd have to know if it's increasing or decreasing.
Mm-hmm. Well, yeah, and you can kind of analyze that too, because here, so I'm gonna what I color in green. So right there, your first derivative graph. So the slope of the first derivative graph is decreasing, and then at x equals -2, it changes, and then it goes to increasing.
Yeah.
And then it switches again, and the slope of the first derivative graph then goes to decreasing again, or negative slope. And then at x equals 1, it changes again, and now we've got a positive slope. So anywhere your first derivative graph changes signs or changes slopes, that's where you're going to have the POIs.
Yeah.
Okay. Now, if you wanted a max or a min from the first derivative graph, so like right here at -3. So what you want to kind of do is all of this part up here that I just colored in purple, all of that is where the first derivative is positive. So your function is kind of going up. Does that idea make sense? And
yeah, that makes complete sense to me.
Yeah. And then after -3, then it dips down and the function is now going back down because the first derivative is negative. So we would actually have right here at 3 or -3, we would have a max right there, a relative max. Because we
on the normal function.
On the normal function, yeah.
Yeah, that makes sense. I mean, yeah, because the derivative is 0, so you're going to have a max or min.
Right. Well, not always.
No.
Yeah, why? Because like over here, what would be going on over here at x equals 1?
The derivative is 0.
There.
You'd have a I don't know, you'd have a max or min on the normal graph.
Okay, well, let's kind of take a look at this piece here. So at x equals -1, you're going to go from negative to positive because you're below the x-axis. So your first derivative is negative right here, and then you switch over and then go above the x-axis. So if you're going from below the x-axis, if you're decreasing and then you're increasing, you're going to have a min.
Okay.
1. Now this guy over here at that spot at x equals 1, both times you're above the x-axis, so you're not going to have anything. Because that's like you did your sign chart and you're like, okay, here's x, here's f prime of x. So at 1, you're above the x-axis and on both sides of it. So you'd be increasing and increasing. So there's no change in the slope at all. So at x equals 1, you wouldn't have a max or a min.
Okay, got it.
Does that make sense?
Yeah.
Cool. So and that kind of goes along with this picture right here. It's the same idea. You know, it says where are your critical values? So even though you cross the x-axis right here at -3, again at -1, and you bounce on the x-axis at 1. So those are your critical values. All three of them are going to be critical values. But the only ones that are going to be max or min is when you cross through, when you pass through the x-axis.
Oh, okay. All right, that makes sense.
Yeah, and the way that you pass through, so you have to kind of analyze and go, well, right here is above, and then right here is below. And then again, this is going to be above the x-axis, and then over on this side, we're still above the x-axis.
Okay.
So if we're above, those are plus, and if we're below, then that's going to be minus. So if you're going to go from, you know, your first derivative goes from positive to negative, so you're increasing, then you're decreasing, that's why that part is going to be a max.
Okay.
So does that make a little bit more sense on there?
Yeah.
Yeah, cool. Awesome. Now, somebody put down how to do the derivative on the calculator without doing, you know, without actually finding the derivative. And this is pretty straightforward right here. So in y1, you would put whatever the original is that you want. And then in y2, so you remember how to get to this button right here, this dx? Hey, good morning there, Anne Marie.
Oh, hi.
Hi. Hey, Joel, good morning. Hi, Dee. So this piece right here, ddx, so on that, you're going to hit math 8. So to do that piece, let's do math.
Well, I'm trying to add this to my calculator too.
So yeah, so you just hit the math button, and then number 8 is the one that does the derivative. And then the trick with that one is when you, after you input that, you've got to make sure you put x equals x for that instead of x equals a number. So right here on the end, you're just going to type x equals x. And then this guy right here, you get to there by going into your, so on your calculator, you're going to take a look at that piece. You just hit your bars menu. And then arrow over to y bars. And then the first thing is function. And then whatever, usually we put it in y1, so you just hit enter. And that would take the derivative of whatever the function is that you've got in y1. But the key is when you go over here at the end, make sure you put, you know, x for your variable. And that way it'll graph the derivative for you automatically, and you won't have to actually have to calculate it. So there's now in Google Class, so let me show you guys this, because a couple of people wanted to know, like, you know, practice the justification phrases. So
Wait, before we...
Oh, go ahead.
Wait, I have a question. To finish that graphing one, do we just graph and do point of intersection?
To do what?
To find the limit?
Well, if you wanted to find the limit, what do you mean by find the limit?
I'm sorry, I meant derivative.
Oh, to find the derivative?
Yeah. So we just do graph and then point of intersect?
No, what you would do is, if you want to just graph the derivative, then you would turn off the other function. So you just go to the top and see how the cursor is blinking on the equal sign.
Mm-hmm.
Yeah, if you arrow, so if you hit enter and then arrow down, that'll turn off whatever that function is. So then if you do zoom 6, the only thing that it would graph would be the derivative.
But wait, but isn't the whole point of plugging it in like that to find the derivative?
Well, sometimes we'll use a calculator to either find the derivative or maybe just graph the derivative if the derivative's too complicated to calculate.
Mm-hmm.
Yeah, I just gave a simple one, you know, a polynomial that we would be able to find that derivative by hand. But sometimes we get ones that are a little more complicated.
Wait, Mr. Muskie,
Yeah.
how would you graph a derivative without a calculator?
How would you graph a derivative without a calculator?
Yeah.
Oh, well, to graph it without a calculator, well, you kind of analyze the function a little bit and see where's the function going, increasing or decreasing. You'd analyze the slopes.
And you do that with the first derivative like test.
Mm-hmm. Yeah.
Oh, the sign chart and the
Yep.
critical
Yeah.
values? Okay.
Yeah. So, but anyway, just real quickly, I wanted to show you guys. So I put a link in Google Class for you for the to practice the justification phrases.
I
And
like that.
Yeah, and if you go to classwork, one way you can kind of narrow that down. So over here on the left, you'll see all of the topics. I put it in the AP review. And then there's a link there that just says the AP Calc justification phrases. So then when you click on that, that'll be the really specific things to say. And again, you've got a couple of pieces down there for proving max, min, first derivative test. So more or less you do your sign chart, right? And then you would write either this phrase right here, you know, f of x changes from negative to positive. You've got to explain how your derivative changes and the x value. So there's two different ways you could say that. So that goes over all the relative min, relative max, and then also the increasing, decreasing. And then the second derivative test parts too. Like if you wanted to do that for max or min, or if you're going to just do concave up, concave down. So that's going to give you all of the phrases in there kind of in one spot.
Can we ask you like questions or
Yeah.
do we? Okay, so if the second derivative is positive, does that mean f of f prime of x is increasing?
It doesn't mean that, oh, if the second derivative is positive, does that mean f prime of x is increasing? That's a good question. Let's take a look at that. Because we're going to do, which one?
Because I remember the circle little thing that we had on our notes.
Right.
And if it was positive, it could be either decreasing or increasing.
Yeah, so if you think about this kind of piece right here, or actually, let me just go here with it. So you can have this, that over there, or you can have this piece or this piece. So each one of these on the top are going to be concave down because they're kind of like the parabola that's shaped down. So that means your original function will be concave down. But then the parts on the bottom that are kind of like a cup, they're going to be concave up. So these guys down here would be concave up. But then your tangent line, you know, you could either have a tangent line right here or right here. Both of those tangent lines is when your first derivative is positive.
Could I ask a question?
Yeah, Jess, you good with that though?
Yeah.
Yeah. Okay.
Oh,
Yeah.
they're both increased. Okay, wait, I need to take a screenshot. Okay.
So if the first derivative is positive, that means that it'll be increasing?
Well, it depends, because you could have the first derivative could be positive and concave down, or you could have the first derivative be positive and concave up. It kind of depends. So let's kind of take a look at maybe one like this, because sometimes you might have a question that's like this, where it'll say for which curve are both f prime and f double prime negative. So you want the second derivative to be negative, which means it's going to be concave down, and then you want the slope to be negative because that's the f prime part. So if I look at this guy right here, you know, it's like my first derivative, I'd be increasing right up to that spot, and then I would switch directions and go down here. So I change. So I don't have a negative slope the whole time. So this guy right here, for choice B, yeah, the whole time I'm negative right there. And then this one right here is the concave up part, because my first derivative is positive. Or I've got a negative slope right there, but this would be my, instead of being concave down, this part's concave up. So that guy.
When you say negative slope, like obviously it's decreasing, but is it when it's below the x-axis that it's negative, or is that just evaluating how the first graph function would look?
No, it's just evaluating how the first function would look.
Oh, okay.
Yeah, because all these are possible original functions here.
Mm-hmm.
And so like on C, that whole time my slope's positive there, so that guy's gone right off the bat. And then same thing with D, like everywhere right here, my slopes are positive, but they're just getting positive. They're starting to get less and less steep. So even though my first derivative would be positive, it would be increasing at a decreasing rate. And if I look at my other guy right here, so this guy right here, all my slopes here for E, they're all negative. And that's the concave down part of my function. So I could either have one of those, but since I want a negative slope, I want the one that goes like this. So E would be our winner on that one.
So the second derivative's purpose basically is to tell you if it's concave up or concave down.
Yep. Yeah. That's the main purpose. You could also use this.
You can use it to find min and max too, right?
Yeah, you could use it to find min and max too.
Because if it's concave down, then it'd be a max.
Well, yeah, and that's where when you do that, so if you have a function, let me just kind of make one up here real quickly. So you had f prime of x was, say, x times x minus 4. Then you know you have, these would be your two critical values. And then you take the second derivative. Once you get your second derivative, you would plug in 0 and plug in 4. And depending on what answer that gave you, if your answer was positive, then that would tell you whether you have a max or min, and depending on if that was negative. So you basically just plug in your critical values to your second derivative function.
And then depending on the sign, it'll be concave up or concave. I mean,
Right.
max or min.
Right, yeah. You got it. And that's where it's kind of, it makes sense a little bit. Like if f prime of, say your second derivative, if it was greater than 0 or less than 0. So say you plugged in 0 and that ends up being bigger than 0. Like you get some value, you know, say that was 7, which is greater than 0. So if your second derivative is positive, that means it's which one? Concave up or concave down?
If it's positive,
right.
Concave up.
Okay, so that's going to be concave up, which means it would look like this, you know, look like a parabola that opens up. So it would make sense that that guy right there would be a min.
Yeah.
And then similarly, if you plugged in 4 and say you got like negative 10 or whatever, some negative value less than 0, that would be concave down, which means you have a frown, but then up here, so that would kind of make sense that that would be a max.
Is this the second derivative test?
Yeah, that's the second derivative test for extrema.
All right, and so these are global min and max?
That would be in the interval that, yeah, usually you're given an interval, and then it would be, you know, an interval to work with, but if not, it would just be a relative min or max.
Okay, so if it's an interval, it's global.
Yeah, if it's an interval, if it's a closed interval, and that's what the EVT guarantees. So if you have this, then that'll have a max, an absolute max or min. But if you have this, then it'll be a relative max or min.
All right, let's just write this down.
Yeah. And this is being recorded too, so if you want to go back and replay it later because you're really bored or whatever, you can always go back and take a look at it.
All right, that's cool.
So I have a question. I don't really understand how to find inflection points. Could we go over that?
Yeah, for inflection points.
Yeah.
So basically, what you're going to do is take the second derivative, get down to the second derivative function. So say your second derivative ends up being something like this, x, and then say x minus 8. And that was just what our values were. So when we plug that, if we plug in, we find our two zeros, we get 0 and 8. So you'd make your little sign chart. Let's see, 0's there, 8's there, and then you would just test it. And you plug numbers in, you know, between 0 and 8, 4, 0, and before 8. So like if I plugged in -3, let's see, if we plug in -3, the first thing I would have like -3 times -3 minus 8. So I'd have a negative times a negative, which will give me a positive. Does that make sense?
Yeah.
Okay. That means my function, my original graph, is going to be concave up.
Oh, okay. That's where the original graph comes in. Okay.
Right. And then between 0 and 8, so if I plug in 2, so I would have 2 times 2 minus 8. So the first thing's positive, the second thing is going to be negative. So then I would have, that would be concave down.
Concave down.
And if I plugged in a number bigger than 9 or bigger than 8, then they're both positive, so that'd be concave up.
Mm-hmm.
So I would have, so these two guys right here would both be points of inflection.
Oh, okay. Because they're both because they're positive to negative and negative to positive.
Right, and that's what you would say, you know, and that. So let me kind of go back to the justification part on that.
How would you justify? Do you mind walking me?
That's a good question. You would justify it like this. So let's see. There's a point of inflection at x equals whatever the value is.
Yeah.
Since f prime of x double prime changes from, and then you have to just, so it kind of sounds like the same justifying for when you do a max or a min using first derivative test.
Yeah.
It's just, but you just switch up those couple of little points on it. There's a point of inflection. Instead of max or min, you'd say point of inflection. At x equals 3, so if this were your sign chart, that's what you would have on here. But at -3, like if your sign chart were this right here, what's on the screen, you'd only have a point of inflection at x equals 3.
Yeah. And is this on Google Classroom, the AP Calc justification phrases?
Yeah. I put those on there. Oops, where to go with that? So I put it in an AP review piece and then just called it justification phrases. So if you want to search over on the left-hand part of the pane, that'll, and just click on AP review, that way you just see that. Or if you look into your stream, you'll see it as a second thing down from the top on the screen.
This has been helpful, but I have to leave. Thank you, Mr. Muscarella.
Yeah, absolutely. If anything else pops up, so on the other thing is that AP style review. So these are actually.
I did that.
Oh, you already
Super
did
helpful.
that? Cool.
Super
yeah,
helpful.
And everything that you see that's got like 2 stars by it, that means it's an actual AP question.
So is position, speed, and velocity going to be on the test?
No, they're not going to be on. No, PVA aren't going to be on there. Just the relative extremity and so the first 2 pages, don't worry about those.
All right.
So what's going to be in the first half of the test and what's going to be in the second half?
Well, the first half is going to be calculator and the second half will be non-calculator or vice versa.
Okay.
Yeah, because there's 2 parts to the test, calculator, non-calculator. So we'll do one part one day and the other part the other day. So basically everything in chapter 3 is going to be on there.
Even the miscellaneous unit?
Say again?
Even the miscellaneous unit?
No, not that. It'll just be first derivative, second derivative.
Okay.
Yeah, concavity, just those pieces will be in there.
Okay.
And then let me see. So what other kind of stuff did you guys want to go through one like this?
Yeah.
And talk about this? Because this was on I think the 3.5 worksheet. So let's kind of talk about this and go through this here real quickly. So the first thing, let's talk about the points of inflection. Now, when you read this, and this is where we always have to slow down because so many people will make a mistake, make sure you read it to know the picture, what the picture is. Sometimes they'll put it in words and sometimes they'll put it right there in the graph. So when they do that, they're trying to really make sure that you understand, like, hey, this is a derivative graph, not the original function. So the points of inflection, I'd have one right here, down here. So they're just going to be the max and your mean of your first derivative graph. Does that make sense?
Yeah.
Why would those be points of inflection though?
Because that's where the slope is 0.
Yeah, that's a really good way to look at it. The slope of f prime is 0 right there. Good. So that's equals 1, 2, 3, 4, 5, and 7. And then if you so let's kind of go to this piece and take a look at this, the concave up intervals. So if I looked right here, and right there, and right there, those are, I got a few minutes. Those are the intervals where our function is concave up.
Because it's increasing?
Because your derivative graph, has a positive slope.
When you're looking for intervals where the function is positive and negative for, because this was one of the first derivative homework, and I'm not sure if I got like that right.
Mm-hmm.
Like, how would you enter that?
So, are you given a derivative graph, or are you given the original function?
It was the derivative graph, and you were trying to find the positive and negative for the original function.
Oh, okay, cool. So your positive part here. So your original function. So I'm going to highlight this part in blue. Anything that's above the x-axis.
Right.
That's where your first derivative would be positive. And right here, your first derivative is positive. Are you okay with that idea?
Yes.
Right. So all those blue regions that I just colored in, that's where your original function would be increasing.
Okay.
Okay, and that's going to kind of lead into this a little bit. This spot right here that's below the x-axis, that's where your original function would be decreasing.
Okay.
So then
Wait, so where it's where the slope is like above 0, that means that the original function is increasing?
Yeah.
All right.
And what if it's like flipped? If you're given the graph of f of x and you're trying to find where it's positive and negative for f derivative of x.
Oh, okay, yeah. So if this were, say this were your original function, but that's just f of x. Anywhere your slope is positive, so right there, and right there, those would all be your increasing intervals. And then your decreasing intervals would be right there and right there.
Well, wait, can you explain that again? Sorry.
Yeah, no worries. So let me just kind of start this part over. So if you had a function that was graphed, and you just kind of looked at the different regions, like right there, and right there. That's where your original function has a negative slope, which means f prime of x would be negative. Your derivative would be negative.
But those values themselves, like the last two purple spots, those would still be increasing because x values are above 0.
If this was the original function, no, that would just we need to go a little bit further to figure out whether that's going to be increasing or decreasing. But with the purple values, all of those are where f prime of x would be negative or less than 0.
So you can't determine where f of x is increasing or decreasing by looking at the derivative graph?
No, you can determine where f of x is increasing or decreasing by the derivative graph. So like on this guy right here, on the one that's the whole screen there where they give us a derivative graph. So this purple part right here down at the bottom, that's where f of x is
Because it's below the x-axis.
right. That's from 6 to whatever it is, 8. But everything
But-
above that,
Yeah,
Mhm.
is increasing.
yeah.
So
But
the purple
because
part-
we've got this one spot here at 4, you'd have to step over that. So we'd go from 0 to 4, and then with 4 to 6, all of that is where f of x is increasing.
Okay.
So just the process to find both, if like the order of the graphs are switched, that's switched, like if that makes sense.
Yeah,
Okay.
And do you always use soft brackets when
Yep.
saying the intervals?
yeah, always.
Even with positive and negative.
Yep.
Okay.
Is there, why is that exactly?
Well, because you can't necessarily say it's where the concavity switches off or a slope switches off. So you can't say that it definitely changes at 0.
Okay.
Because at 0, that's where you're either going to have a horizontal tangent line, or maybe it's not going to be defined because the function is not always going to be differentiable, or the slope will be 0 at that spot. And then let me go over one more with you guys real quick before this kicks out, and that's this last guy right here. Order from least to greatest, f of 3. So if you take a look at where 3 is, 3 is right. F prime of 3, we know that that is 3. Everybody okay with that?
Wait, what?
F prime of 3 is 3. Because if we look on our graph, we just look at the curve. Oh, not 3, sorry, 2. That's just going to be 2.
Okay.
Okay. Now f double prime, because we've got a horizontal tangent right there, what's the value of that derivative going to be? You have a horizontal tangent, and your derivative is going to be
0.
0. And then f of 3. Now, this is the part that kind of takes a little bit of thought. Now, so that means the y value. So this whole time that we're up here, we're just increasing and increasing and increasing the whole time until we get to 3. So we're increasing a whole bunch, we're increasing a whole bunch, and then we stop increasing. So that number is probably going to be a lot bigger than 2.
Oh, yeah, I get it.
So if we had to order those from least to greatest, then we would have, let's see, f double prime of 3 would be less than f prime of 3, which would be less than f of 3. So there's definitely going to be one like that on your test.
Okay.
So, but yeah, so it really makes you think a little bit on that.
All right. So second derivative is going to be the horizontal tangents of the first derivative graph.
You got it. Perfect.
That was helpful.
Yeah. The second derivative, so like right here, we would have, our second derivative would be 0 at x equals 5.
Yeah. Okay. And the second derivative, like, just, like, wouldn't exist anywhere else but the horizontal tangents?
On this graph, yeah, because we don't know if anywhere we've got a vertical tangents anywhere, but just looking at the picture we have, because we're only going 0 to 8. So that's the only spot we look in.
All right. So the only way that the first derivative would be lesser than the second derivative is if it was, like, below the x-axis.
Mm-hmm.
Okay. Cool.
Yeah, because say we were taking a look at 7 instead. So we know the derivative here is 0. Which
Yeah,
means
0.
F prime of 7 would be 0, but we know that the F prime of 7, we know that value is -1. And so our first derivative would be less than our second derivative value at x equals 7.
All right.
Cool stuff. All right, if there's anything else you guys think of, you know, just pop in tomorrow morning. I don't think we'll have a delay, but one never knows. And if we do, we'll just adjust. We'll just adjust. It'll be okay.
Okay. All right.
Class
Thank you.
tomorrow reviewing, right?
Yeah, as long as we've got a full class, yeah, we'll spend a little bit just reviewing and going over everything, and then we'll take the test the second half.
Should we have a delay? What would it be like?
I don't know. It depends how they do the schedule for the day, so we'll figure that part out.
Okay.
Yeah, because chances are we'll have more than 45 minutes in the class, so I want to make sure you have 45 minutes for the test part, and then whatever other time we have we'll just review.
Okay.
All right, good stuff.
All right. Thank you.
Yeah, thank you guys for being here today. I appreciate it. Enjoy the rest of the day, and who knows, maybe tomorrow we'll either be delayed or off then too, but I think based on the weather, we'll be in tomorrow for a full day.
Thank you so much. This was very helpful.
Yeah, absolutely. Anytime. I'll catch up with you guys tomorrow.
Yeah.
All
All
right.
right.
Peace out.
Bye.
Bye.
Bye.